Hey guys, we'll start here in a few minutes, just waiting for some more folks to show up into the class. Why don't you speak up and let me know that you're here. I see Owen, Emma, and Caitlin. Just want to make sure that audio is working.
Hello, good morning.
That sounds good on mine.
Okay. While we're waiting, I'm curious, how many of you guys are going to school tomorrow to pick up stuff out of your lockers?
I don't got anything to pick up, so I'm happy about
I don't
that.
have a locker either, so I'm not. Yeah.
Oh, so you're good to go.
Yeah, I sold my
Yeah,
locker and closed the doors.
Miss Husky actually told me yesterday on our softball meeting call that every single time a teacher or anybody has to walk into the building, then they have to re-sanitize the entire place.
Really? I didn't know that.
Yeah, so like she said that like her for academic advising, she has her junior slips in her office and she can't go get them until, I guess she'll get them tomorrow, but she said unless there's like a scheduled time that all teachers can go, then she can't go and get them because the whole building has to be sanitized.
Huh. I didn't know. Wow.
But yeah, that is kind of crazy.
Hey, Captain.
Yeah.
Did you say we were going to go over formal chart a little bit today, or
A lot.
Okay.
A lot.
Okay.
I'm not going to spend as much time on the upfront, so I can do a couple more formal charges. I'm also going to record this, or I am recording it. So just in case some people can't watch tomorrow's, where
Okay.
we'll also go pretty deep into it.
All right.
Morning, Cap.
Good morning. And who was that who was saying good morning?
It was Cadence. Hello.
Oh, hey.
Hey, Captain.
Good morning. Good morning. Okay, while we're waiting, or while we get started, the first thing I'd like to do, Megan Jolly, what is that visual you have on your camera?
I didn't think that was going to come up. It's like there's a park in Utah where during Christmas time they put lights up, and I took that photo like 5 years ago,
That's
and I
great.
never changed it.
That's okay. All right. Very good. All right, good. All right. Are there any overall questions that people have? Yeah, I know Conley, I see she just signed on. I know she's going tomorrow to get stuff out of her locker. Is anybody else going? I've heard a few folks, most folks are not.
Well, I would go in, but they said that it was only for necessary items
Yeah.
and nothing that I really have in my locker. It's like all stuff that was from Miss Griffin's class, and I had her last semester, and I don't even want to think about that stuff, if I'm being honest.
Okay. All right, sounds good. Very good. All right. Well, it looks like we have about 10 folks so far. So I'm going to, first of all, are there any other broad questions? We talked about, picking up our stuff tomorrow and that sort of thing. So
Did I miss anything not being in a meeting yesterday?
please.
Did I miss anything not being in the meeting yesterday?
No, today's meeting is slightly different from yesterday's. For example, I see a couple folks who are on twice. They were on yesterday and today, so they can hear the lesson twice. Plus, I'm going to go a little deeper into formal charge so that folks can see that. And so my lesson today will be very similar to the lesson I give tomorrow. So without any other ado, here, let me just kind of jump into it. Let me make sure first I'm sharing. Very good. So you should see, come on. All right, you should see a PowerPoint, which is a tracker page called Drawing Molecules.
Yes, sir.
Okay, good. So it must be working. All right, so basically there's three parts of this discussion. I'll be asking questions as we go. Just go ahead and speak up when I ask some general questions. But basically, I'm going to give you some of the basics on drawing molecules. I'm then going to talk about Lewis structures. This is very different than what you were taught in junior high school and what I taught you last summer. But you'll use this skill set pretty much for the rest of your life if you're going to be a STEM major. And then we'll talk about formal charge. Generally, this stuff, the bottom two things are pretty much all of this is not something that a regular chem student takes, right? This is all, advanced chem, AP type stuff. So kind of jumping into it, as you know, or hopefully you know by now, I show a link at each part of my section breaks showing a video that I've watched that I think is helpful. This one here has Hank Green's explanation of the basics for Lewis structures and explains double and triple bonds and that sort of thing. We know that there's lots of different ways that we can draw molecules. If you are choosing to major in chemistry or biochemistry or chemical engineering, this one that's down here in the lower right-hand corner with these ribbon molecules, ribbon model, that sort of thing, that's the sort of thing you see the organic folks doing. I forget which compound that is, but actually that is the shape of these things, and that's similar to, I don't know if that's an enzyme or a protein, but that geometry is, of course, how things lock together, like we learned in maybe junior high school, or you learned in AP Bio if you took that. You may have actually seen drawings of molecules like that. But the one that we're interested in today is really Lewis structures, and here's a real simple one that isn't any different than what you've learned, when I taught you this last summer. These are called structural formulas. Generally, you won't be doing any structural formulas for now on in my course this year or next year. That's where you just put the bonds like this and you leave it at that. And the reason why is it turns out, this has been a big secret, but the unshared pairs, the little electrons that are not being shared, are a big deal. Who knew? Yeah, they're a big deal. So we'll talk more about that later. We already know about the octet rule. And we know that the octet rule is because you guys now understand how orbitals work, that it's made up of the two s orbitals and then or I should say the one s orbital, which has two electrons in it, of course, and then of course the six p orbitals or p electrons. And so 2 + 6 is 8. And what we'll talk about when we get to molecular geometry is that does anybody remember the shape of the s orbital?
The sphere.
Was it like a dumbbell?
Close. Somebody said sphere. They're right. And if somebody was probably looking at P and they said dumbbell, and they're right. The P orbital is a dumbbell, and of course the S is a sphere. Well, I remember when I was a kid and I learned about the S and P orbitals. It's like, well, how does that work? How do you make a compound that looks like that when we know, like, for example, this is a bad example because I don't have one here in front of me, but like methane is, we know, is a tetrahedron, right? I don't see any place for a spherical orbital, and I see no dumbbells in here, but somehow these things bond this way. And so what I haven't told you is that what we believe is that those orbitals are only for unbonded atoms. Once they bond, these orbitals hybridize. They actually change their geometry and shape. And it's actually pretty cool and pretty fun. But we'll talk about that in another unit. For right now, all you need to know is we're going to follow with the old octet rule. We don't worry about inner shell electrons. Why? Why not? Anyway, why don't we care about inner shell electrons?
Because they already have a full shell and they're bonded.
Well, they're not bonded to another atom. The reason why is because only the valence electrons are involved in bonding. The inner electrons, they're already loaded up in there, and they're just hanging out, and there's not really anything that that they're involved in terms of bonding. So it's just the valence electrons. The Lewis structures, the Lewis dot structures, I've had you draw these before, and then you may recall that I've made you put the little lone pairs if they were there and that sort of thing. Single bonds, the way we draw them is this with this dash. No more putting together little dots like you see here. We will leave that behind us, never use those again pretty much for the rest of your lives. You'll just use dashes. As it turns out, these little lone pairs are really, really important. Who knew? More about that later. So the single bonds, of course, are represented by a dash. And so I have a question for you. How many electrons are in this little bond? Right here.
2.
Yeah, there's 2. And so those are the pair, that's the shared pair between these 2 hydrogen atoms, right? So you can see right here, you can see these 3, or excuse me, these 4 lines, each one of them represents a shared pair. And so we no longer will draw them like this or however, we'll always represent them like this. But what we're trying to say when we draw these things is that's a shared pair. Double bonds are stronger than single bonds. There's only 1, 2, 3, 4, 5 atoms that generally are involved in double bonds. You have to memorize these. They're pretty easy to remember because if you took AP Bio, you had to learn SNOPs or CNOPs or whatever the heck you call it. But these are the only elements on the periodic table. In fact, I'm going to need this. I might as well just call it up. Let's see, that's AP. Let's open that. Open up periodic table. There we are. All right. There we are. Let me rotate it. Cool. So CNOPS, these are the only ones that are really involved in double bonds. I have a question for you. Why aren't there double bonds involved in some of these other atoms? There's no reason you would know this, but can anybody guess? Why wouldn't, and the hint is actually in, oh, I beg your pardon, I didn't shoot. I just switched something and I didn't show you that I'd switch. Hold on here, just a second. Let me do this. Okay, can you see the periodic table now?
Yep.
Okay, so CNOPs are the elements that can have double bonds. Why is it that some of these atoms down here can't do double bonds? I mean, you know, they have the same valence, all that other stuff.
Are they too heavy?
Well, you're close. They're not too heavy because mass doesn't really matter, but they are too something. Anybody else?
Too big.
Too big. They're so big they can't get close enough to each other to make a double bond. And but these guys are small enough they can do a double bond. So getting back then to, let me see, here we are. Here we are. So you should be able to see the PowerPoint again, right?
Yes.
Yeah.
Good. So you'll see that these, and we'll talk more about this when we get to molecular geometry, but a double bond is actually stronger than single bonds. And can anybody tell me then if it's stronger, what must be true about this bond compared to a single bond? Cadence, what do you think?
Well, it's strong, of course.
It's strong. And what's making it stronger? What possibly has to occur for a double bond to be stronger than a single bond? And remember about Coulomb's law. All chemistry is based on Coulomb's law.
I don't know. It slipped out of my mind. I was just thinking about it.
Somebody else?
Is it the radius is smaller or bigger?
Yeah, so the distance is shorter. So we know 701134. Ooh. Should I let
It's
this
probably
person?
someone from email.
Do you think, is that a number that makes sense to you guys?
Yeah.
Yeah, it's the email.
That's one of
Yeah.
the later ones.
Okay, all right, I'll let them in. All right, so as you get to a double bond, these atoms have to be closer together. And so it takes more energy to break them apart. And the reason why it takes them, because if they're closer, remember Coulomb's law, which has an inverse relationship to distance, you know, it's, what is it? K Q1, Q2 divided by R squared, right? And R squared, of course, is going to be smaller. Of course, it makes the force bigger. So it's harder to break a double bond. So double bonds are stronger than single bonds. Moving on, then triple bonds, what do you think? They're even stronger than double bonds. And only these three elements can form triple bonds. And by the way, I think all this is in your note-taking guide. So hopefully you're following along and you can just write things down as you go. So, you know, the classic example of a triple bond, of course, is nitrogen. The reason why nitrogen, you know, we breathe it in, breathe it out, breathe it in, breathe it out. We know 80% of the stuff we're breathing in is nitrogen gas, but nothing happens to it. And the reason why is that it takes a lot of energy to break that triple bond. So nitrogen, it's not inert, but it's pretty close to being inert. And because it takes a lot of energy for our bodies to break this bond, so it just doesn't happen, thank goodness. So there you go. There's also a triple bond with boron. It's really a trivia thing. It was a chemist came up with this about 7, 8 years ago, making a triple bond with boron, which is a little bit of trivia. So you can see then that which of these bonds are strongest. Obviously, it would be acetylene is strongest, which is really weird because many of you, when you go to college or in your subsequent jobs, you're going to work with acetylene torches. And they're really, really fun. And it's very strange because they put off a lot of energy. But you're going to be confused because, wait a minute, Captain Pursley told me it took a lot of energy to break this triple bond. So why is it if I broke this triple bond, it costs a lot of energy, can I do this kind of stuff? This is an American Navy sailor. He's burning an acetylene torch, and it puts out a buttload of energy. With this triple bond, you would think it would cost a lot of energy, not release it. And the answer, just in the interest of time, is that how many bonds are we breaking there? Well, there's 3, so that creates 6 bonding sites for the carbons then to bond to something else. And every time a bond is formed, energy is given off. So even though it costs a lot to break this bond, you give off even more when those things bond with oxygen, which is pretty cool. There's a few things called quadruple bonds, and I know nothing about them, but I found it on the internet. I thought it was kind of interesting. So pressing on then to Lewis structures, there's a couple of videos on here. If you are like me, you probably have already started or will start to use some of these online videos. You know, my AP Chem students love Wayne Breslin's stuff and also Tyler DeWitt's. You will be using those videos a lot. In fact, a lot of you guys will be lazy like me. You'll be saying, okay, how do I do this Lewis structure? Screw it, I'll just start. In fact, I'm just gonna do this. I'm gonna show you something. I assume you cannot see my web page just yet, right? You're still looking at the PowerPoint?
Yep.
Yes.
Okay, so what I'm going to do, I'm going to change it to this. You should be able to see this, okay? Everybody got it? Everybody see a web page? Okay, watch. Lewis structure, Lewis structure, look at all these, they've already started appearing. We'll do it for, let's do something exotic like sulfate, SO4 2 minus. Crap, 2 minus. All right, so you just go ahead and do this, and you will see tons and tons of videos that explain what I'm about to teach you about how to do the Lewis structure for sulfate, including this idea of formal charge, which I will teach you here in a few minutes. And so a lot of you guys and my AP Chem students started doing this too, of course, when they were taking advanced chem. Of course, they tried to do it on their own, and they'll start either watching videos by Tyler DeWitt or by whoever to see, here's one by Wayne Breslin. that explains, well, great, we learned about this. Yeah. Okay. And so, of course, you're sitting here thinking if everything you know about Lewis structures right now, gosh, Captain Pursley, these are really easy. I don't know why you're making such a big deal about them. Well, they're more complicated than you actually realize. So I've been giving you very, very simple ones. But there are lots of videos on this, and I'd be recommending these videos even if you weren't taking this course at home, because it takes practice. And sometimes you're at 10 o'clock at night, you're like, I cannot do SO3. I can't do it. I don't understand how they're getting this. Well, you just type out Lewis structure SO3, and there's somebody out there, mostly it's Tyler DeWitt or Wayne Breslin, who will explain to you how to do it. So here is the magic formula that you'll use for the rest of your lives. This is the formula, or the cookbook for drawing Lewis structures. You take the electron inventory. Trust me on this, the electron inventory is the most important thing. And if you are, would everybody agree in here that Megan Jolly is a pretty bright person?
Depends on the time of day.
Oh, that was a very wise comment. Was that Owen? Very wise. Okay.
We both said that, Captain. It's okay.
All right. So Megan Jolly is a pretty bright person. So Megan's going to be her worst enemy, because she's going to say, oh, I know, I can do this electron inventory in her head, right? So that's what she's going to do, because she's, you, my friend, are the easiest person to fool. Somebody who, and in fact, often I will say, oh, no, I don't have to do electron inventory. I can do it in my head. And then you're just going to screw yourself over. You then will draw because you'll jump straight to the skeleton drawing, and then the wheels are going to fall off later on. You add the outer octets, you add the inner electrons, you then do an inner octet, and then you do formal charge, and then you do ionic form. I know none of this makes sense to you yet, but it soon will. All right, let me first talk about 3 octet rule exceptions. The first one is electron. There are some rules, and you already know 2 atoms that don't follow the octet rule. Anybody know what they are? Perhaps somebody who wasn't on yesterday's call can tell me which atoms don't follow the octet rule.
I actually don't know.
Well, look at the periodic table. I'm going to probably start asking people to, let's see, where is it? Right here. Here's the periodic table. You guys can see this. Is there anything on here that looks like it might not follow the octet rule?
The transition metals.
That's actually a pretty good idea. It's not the one I was thinking of. Please?
Hydrogen?
Yeah, that's it. So hydrogen is one of them. What's another one?
Helium.
Yeah. And as it turns out, 2 other ones that don't follow it are beryllium and boron. And beryllium and boron, weirdly, even though they're metals, start behaving with a covalent type sharing scheme. And in fact, if you've noticed, when I was giving examples of ionic compounds, I deliberately avoid the discussion of beryllium and boron, because they behave so strangely and more like nonmetals and do covalent bonds, but they don't follow the octet rule. So let me go back to that. Let's see, where's my, there we are. All right, so the first one I mentioned was hydrogen and helium. The next 2 is beryllium. Here's how beryllium chloride would, or dichloride. And notice that even the nomenclature is more like a covalent compound, which is very, very strange, because I've beaten into your heads that these guys are metals. And then, of course, here's boron. And it also behaves with this non-octet rule. Here it's 4 electrons, here's 2, here's 4, and here's 8, and this boron, or 6, and this boron is just happy as a pig and you know what, just with 6 shared electrons. Okay, so, which by the way, the shape of this thing, which we'll talk about later, then, because these guys repel each other, this is actually closer to the shape of what beryllium trifluoride will look like. And in fact, later on, you will start, it'll bob bother you to draw this because you know it looks like this. Not yet, but soon. All right, then Lewis structure, there's also very strange ones, and I'm going to do phosphorus pentachloride for you, okay? So you should have, all right, got it. All right, so let me go to, hello. I want to do a whiteboard. Okay, so I'm going to do, can you see my whiteboard?
Yeah.
Okay,
Yes.
so I'm going to do phosphorus pentachloride, all right? Unfortunately, I don't have a touch screen, so I'm writing this with my mouse, so I look like I'm like, what, 7-year-old writing this. All right, so I'm going to go through the process of writing or drawing the Lewis structure for this. The very first thing that I'm going to do is take the electron inventory of these little devils. All right, and the way you do this, Megan, I'm speaking directly to you about this, is you don't do this in your head. What you do is you write down the number of valence electrons that phosphorus has. Somebody tell me.
5.
Yep, same as nitrogen, 5. And then how many phosphorus do we have in this problem? Well, 1. So I have 5 electrons to deal with. True? True. Then I have chlorine, and chlorine has how many valence electrons?
7.
Yeah, 7. How many of these little guys do we have? We have 5. So 7 times 5 equals 35. And already I'm breathing a little sigh of relief, because you will soon learn that if these guys don't add up to an even number, all hell's going to break loose. You need even numbers. All right, so here we have this 40 electrons is what I have to deal with. All right, so this is going to be pretty easy for us. The next step is draw the skeleton. Well, there's phosphorus. Now I'm going to draw a chlorine there. I'll do a chlorine there. I'll do a chlorine there. I'll do a chlorine there. And I'll do a chlorine there. And then I'll put, oops, darn it, let me erase that. Darn it. Okay. So, and then of course I draw one of these little guys here and here and here and here. Okay, I know it's ugly, but you get the idea. The next step, if you look on your note-taking guide, is you then what I call put clothes on the ligands. These are called ligands. The ligands, that's the things on the outside. So I'm going to put clothes on these little fellas. That means fulfilling the octet rule. And, you know, here we are. These are pretty ugly, but, you know, cut me some slack. I'm doing this on a mouse, not a touch screen. So there you have, now we inventory these little guys, and we count up, there's 1, 2, 3, 4, 5. 5 times 8 is 40. That's what I have here. Is the octet rule fulfilled for phosphorus? Well, it's actually overfulfilled. In addition, instead of having the octet rule, there's actually an additional shared pair in here, and that's perfectly fine. I now, and because there is no ion, I don't have to do anything else on that. So that's a very, very, very simple way of drawing these little guys. Okay, so yes.
How does that work if that means there's 10?
Yes. All right, so let's get back to the exception so I can explain it to you, okay? Good question. All right, let's see. So I'm back to this. I want to go here. All right, so now what I'd like to talk about is how the heck can this occur? Well, as it turns out, after row 3, we know that the p and s orbitals hybridize, and that's how we get the octet rule, right? There's 3 p's and 2 s's, right? But after row 3, if you have the periodic table in front of you, I'll show you this again here. Oops, I've got to do it this way so you guys can see it. You should be able to see the periodic table. And you can see in row 3, we know we have the, well, first of all, row 1 and 2 and 3, in fact, all the rows, this is the s orbital, here are the 3 p's, and they can hybridize. And that's perfectly fine, and they do that, and they end up being bonding orbitals. And, but as you go down here, what orbital is available, even though you can't do much with it until you get to the next row. You have S, S, P, P, but what's down here? What orbital is this?
E.
D. Give me a number for this D. Is it 1D, 2D, 3D, 4D?
That is
3D.
It's the 3D. Aha. Well, as you start filling electrons in these atoms, as you get further to the right, what happens is this D orbital becomes available for hybridization. And again, I teach this every year. You're like, what's this hybridization thing Pursley's talking about? That's another unit. We still just have to master drawing these darn things. So what happens is the 3D orbital becomes available to then become a bonding orbital, and you violate the octet rule. So you'll see that with sulfur and chlorine or selenium and bromine, those sorts of elements. You'll never see it with oxygen or fluorine. These only follow the octet rule. They cannot be violated because there is no 2D, so there's no way for that to occur. Okay, so let's go back then to my PowerPoint. I will talk about this more later. When I first started teaching this, I never shared this, but here's phosphorus, which we know has 2 s electrons and 3 p electrons. We know then what happens is in a bonding situation, one of the s electrons migrates to the 3D and then hybridizes into the sp3d. Don't cry, don't lose any sleep. That is not part of this lesson. I'm just giving you a little hint of where we're going. This is for later on for molecular geometry. But you see now that we now have not 1, not 2, not 3, not 4, but actually 5 unpaired electrons that are ready to get married to some other atom. So that is a very strange thing. So expanded valence shells at n equals 3, most common are silicon, phosphate, sulfur, and chlorine. And the reason why is because they have empty d orbitals, and they bond to small electrolyte negative atoms like fluorine, chlorine, and oxygen. So there you go. So let me do this one. I want everybody first to start off, everybody on the call, write down or do an electron inventory. Okay, and so you should have a piece of paper, note-taking guide, something. I don't know. Let me go to what's this? Iodine tetrachloride ion. So you need to write that formula down. I'm about to make it go away. So because I'm going to go back to my whiteboard. Okay, so clear all drawings. So you should be. I like this one better. All right, iodine. What was it? Tetrachloride. I don't longer have it in front of me. I think it was like that. And then I think there was an ion. I think that's what it is. Right? Okay.
Yes.
So, all right. So everybody do the electron inventory and tell me what you get. Write down how I showed you. Don't do it in your head, Megan. All right. So write it down and you'll see what I'm doing. And watch this structure I'm doing is I'm actually going to inventory the number of valence electrons in iodine and chlorine. And then, of course, because it's an ion, I'll either going to have to add or subtract the extra electrons because it's got some electrons that are involved that are not associated with any particular atom. So iodine, what's that? 7 times what? Okay, I'm going to leave it at this. I want to see what kind of numbers you guys get. When somebody has a number, just call it out. It's okay if you got it wrong. I think Owen, what'd you get?
Like in general or just for chlorine?
No, I went the whole Megillah.
35.
Oh, 7 times 4 equals 28, and then I got 35.
Okay, so you later on will say, holy crap, this is wrong. It can't be 35 because there's no way I can solve a problem with 35. So let me show you what probably happened. We know this is 7, right? And this is times 4, right? So this, of course, is 7. And the reason you got this is you got 28, I think is what that is, right?
Yes.
Right, and that adds up to 35. But you have that little guy. You have 1 electron that's also being added to this complex. And so that gives you this. And so the number actually is 36. There are 36 atoms, and you're about to see why, 36 electrons, and you'll see why in the next step. So everybody now on your piece of paper, draw the skeleton drawing for iodine tetrachloride. Draw the skeleton. Hint, hint, which one do you think is the central atom?
Iodine.
Yeah. Yeah, it's clearly going to be iodine because there's only one of the stupid things. And how many
Is
chlor? Say again?
Do you have to do the brackets for this one?
We are going to do brackets for this one, but we save those for the end. That's if you look at the cookbook, that's the very last step we do. Okay. So we now have iodine, and then we draw a skeleton. In this way, it's a pretty easy skeleton. There's only 4 of these little guys, right? So I'm going to draw a chlorine and a chlorine and a chlorine and a chlorine. Okay, I've just done the skeleton structure, right? Next thing, the next step is put some clothes on. It says fulfill the octet rule on the ligands, or the outer atoms. I forget what it says in my cookbook. I can't toggle back to it, right? So here we are. So we're on this. We have this. I've got some clothes on these chlorines. Okay. All right, so everybody count this. 1, 2, 3, 4. When I first learned how to do this, I literally counted every electron. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Until I figured out, oh, duh, this is 8, this is 8, this is 8, this is 8. So I end up with, of course, 8 times 4, which is, of course, 32 electrons. Okay. The next step on the cookbook says, is the octet rule fulfilled on the inner atom? Yes, it is. So I don't have to do anything with that. Then it weirdly says, add any other electrons to the inner atom. So literally, I do this. And you always add them as pairs. Always add them as pairs. I will not give any student credit if they give me electrons that look like this. All right? Remember I told you even last summer, electrons always travel in pairs. So I will give you 0 points if you give me these 4 extra electrons like this. They must be in pairs, because these unpaired electrons, as it turns out, are really, really important. And of course, when we were kids, we blew them off when we were in junior high or whenever. But it turns out they're really, really important. All right, so I now have 4. And I know this is like totally freaking you out because you're saying, I've never seen a compound like this before. So this is a 36, and that's what I have here. So it looks like I've done a pretty good job. And then I have to put a bracket, as somebody asked just a few minutes ago, and I put a minus there, and that is the Lewis structure for iodine tetrachloride ion. Ain't that beautiful? All right, so let me go back to the PowerPoint. No, let me pause. Any questions?
Yeah, okay, so I am still kind of lost at how we went from 28 to 36. Like, I was watching and it's not sticking in my brain.
Okay, well, there's 7 here.
Yes.
And there's 28 here, so that was 35.
Yes.
Right? And then we know that there is an electron that is added to this, and the reason why we know it is because it has this negative charge. In other words, there is one more electron added to this complex of atoms that, well, this is kind of weird to say it this way, Megan, but it shouldn't be there, right? There's no visit. I mean, what we should have are 35 valence electrons, but it turns out there's one more is added, and because of that, then of course it has a negative charge. And so we have to account for that electron. So for example, if you, one of my favorite problems to do, yes, I will be testing you on it. You can guarantee it. I'll be testing on it 2 weeks from now. That's one of my favorite polyatomic ions, sulfate, right? By the way, which part of the poem, Nick the Creepy Baby Camel, is sulfate?
Supper.
Supper, right. And there's 4 consonants and 2 vowels, all that kind of business. So in this case here, if you added all this up, there's oxygen, There's 4 times, what is it? 6? Is that what oxygen has? I think it's 6, right? 4 times 6 is 24. Sulfur, well, sulfur is a cousin of oxygen, isn't it? So there's 1 times 6. So that's what? 6. And then you think you're done, but you're not, my friend. There's 2 extra electrons that have been added to this little devil to give it this negative charge. So here's 1 times 2. And I have 2, so that total number is, what's that? Was that 32? So that's the problem I need to solve for sulfate for another problem. So you have to add the electrons whenever you, extra electrons if you have an ion. Other questions?
Do you always add the electron, the charge, or can you subtract them?
Oh yeah, that's a great question. Here's one, NH4 plus, okay? So NH4, how many valence electrons does sodium have? I mean, sorry, nitrogen. What is that? 5, I think. This supposed to be a times 1 equals 5. And then, of course, hydrogen has 1, and there's 4 of these little guys. So that's 4. And right away, you should start freaking out because, Jesus, there's no way I can solve something with an odd number. There's no way. This is all about pairs. So, but oh, of course. So in this case, we don't add an electron. What do?
Subtract the electron.
Right, because that's clearly what happened, right? And when you do that, this ends up with an 8. So then I run out of space, but 5 plus 4 minus 1 equals 8, and there you go.
What does it take it from? Like, which electron is it coming from, the N or the H?
I have 2 smart-ass answers for that. You can't talk to me for an hour without something like this coming up. I just can't help myself. One I could say is it costs you a lot of money to do that, meaning go to college and major in chemistry, and then you come back and tell me, all right? But actually, the other reason why is that we don't really know, and I'll explain that when I get to resonance in just a minute. This is the stuff that I'm teaching you in chemistry. Blake will agree with me that as we get further and further into this semester, I'll be teaching you more and more stuff that might be bullshit 3 years, 15 years from now. Okay, so the answer is we don't really know, but we definitely do know that this is definitely what ammonium, that's the ammonium ion. We definitely know it looks like this. We know it's a tetrahedron, and we have no idea which one of these little guys gave up their electrons. But we know that's what it would look like. Okay, all right. So pressing on then to the PowerPoint. Whoops, I gotta share my PowerPoint. There we are. All right. So does everybody see the PowerPoint?
Yes.
Okay. So we just did this one, iodine tetrachloride, and you come up with this very strange looking compound. There it is. The last exception to this is, of course, odd numbers of electrons. If you ever come up without odd numbers of electrons, you've made a mistake. There is no problem that I will give you that has an odd number of electrons. You have to major in chem, and even in AP Chem, I'll give this structure to a student. I'll never have them come up with it, but I might ask them. In fact, it's kind of a well-known AP Chem question, which is, why is it this structure? Why is it that oxygen it seems like it has its octet rule filled, but this one is starving for electrons? And I'm expecting my AP Chem student to say, well, Captain Pursley, the reason why is oxygen is more electronegative than nitrogen. So it's pulling more electrons towards it. Besides that, you'll never have to do an odd number of electron problem. If you end up with an odd number of electrons, you made a mistake. Okay? or I did. I assigned you odd numbers, which, might happen. But so we now get on to this next step, which is resonance structures. Look at oxygen, which is ozone. You'll see that there's actually two different possibilities here for ozone. And here for carbonate, there's actually three different possibilities for a double bond, okay? And so I'm gonna show this, and we call these resonance structures. The answer is we don't know which one of these is the right structure for carbonate, so we say that all three are the correct answers. If I ask you for the carbonate structure, which I'm gonna do here in a minute really quickly, I'm not gonna answer any questions on it because I wanna go on to formal charge. And then you'll have to either draw me these three drawings, or I'll show you another way to use some shorthand that the chemists use, okay? So let's go to the whiteboard. What's this, carbonate? Okay, carbonate, CO3, 2 minus, right guys? By the way, which part of the poem is it?
Is it creepy?
Creepy is chromium. I mean, chromate. Camel. It's camel. Right. So we'll go like this. I'm going to go really quick on this. So that's 4 times 1 equals 4. Here's oxygen. It's got 3 times 6 is 18. All right, and then electrons, you got 2 extra little electrons here. That's 1 times 2, that's 2. So I have 24 electrons I got to deal with, right? So now I draw the skeleton. There it is. We'll put it like this. I've got an oxygen here, here, here. The next step, the cookbook tells me to put some clothes on the ligands, on the things on the outside. So I'll do that. Great, 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 super, okay, there we are, and like this, okay, 1, 2, 3, all right, so now I have 24 electrons, and you're gonna think I'm done, and you're not, because if you look at the cookbook, the next thing says, is the octet rule fulfilled? Well, I would say that it's not fulfilled because I have 2, 4, 6 electrons going on around this carbon, which means that we're going to have to hijack 2 electrons and turn them into a double bond. So I just arbitrarily picked this one. So let me go, boop, get rid of that and that and that. All right, and now I'm going to instead make a double bond. If you count these up, you'll see again, I have 24 electrons, but what's the difference? I now have the octet rule fulfilled for carbonate. All right, yes.
One question. So like the double bond, it would be, since oxygen is more electronegative, it'll take the 4, but then carbon will only have 2.
What happens, no, is that we allocate them, so half go to them and half go to him when we do formal charge. So the way we would say this is this oxygen here has 1, 2, 3, 4, 7 assigned to it. This one has 7 assigned to it. And this carbon would have 4 assigned to it, okay? All right, so then of course to finish, you got to put the brackets, or I won't give you credit for it. You write the 2 minus, and you now have, there it is. All right, that's the Lewis structure for carbonate. All right, and you won't be able to understand these until you practice them on their own. There's no way to master this by watching me doing them on the board or online like we're doing right now. So there's just no way you can do it. The only way you can do it, and that's why I gave you tons of problems to practice with. All right, so, let me come back to, dang it. So I either expect you to draw 3 of these with the double bonds in a different location for each one of these, or you are allowed to do this really cool thing that the chemists do, and I will accept it, which is you can draw 1 double bond and then you draw this. And what you're saying with this is that there is 1 set of double bonds but it can go between any of these three locations. See those little dashes? There it is. So you will use those a lot. Okay? All right. So let's get back to the PowerPoint. All right. So you can see carbonate. There it is down there. 3 different resonance structures. And you'll use this word resonance for the next 2.5 years in AP Physics and also for AP Chem. All right, so you can see here's a location. This is a correct answer, but just as correct as you just have to draw it once for me and put little dashes there. They're saying, you're telling me that CAPT Pursley, sometimes the double bond can be here and sometimes the double bond's here, and I will accept that. Otherwise, I need all 3 of them. Okay? All right. So here's how you would actually write the Lewis structures for ionic compounds. Is you would write the ion for sodium, the ion for chloride, etc. And that's how that works. Then lastly, for formal charge, you're like, holy crap, that's the last step of this. I have examples of these things. And the formal charge cookbook, you can see it right here. For some compounds, as you move along, you're going to see that you want to make sure the formal charge is as close to 0 as possible. See where it says 0 down here? All right, so hopefully you have your note takers and you're putting this in here. And the formal charge is should minus has. And the way I'm going to teach this is just show you an example with one of my favorite compounds, which is phosphate. Okay, I'm first going to show it to you here. And now I'm going to draw it. That's cool. So let me go to phosphate. I'm going to draw phosphate, right? Let me clear this. Does everybody see my whiteboard?
Yeah.
Okay. And refresh my memory. This is phosphate, right? So somebody tell me what that formula is.
PO4 3 minus.
Beautiful, beautiful. And what part of the poem is it?
Phoenix.
Yeah, phonics. That's where I was born, as it turns out. I was born at where my mom worked. She was a nurse at St. Joseph's Hospital. Okay, in Phoenix. And I used to write Phoenix when I was a kid this way. F-E-N-I-X. And later on, no, I thought I was clever. That's right. Phoenix. That's how I thought it was spelled. Okay, so here's phosphorus. Oh, I'm going to do what Megan's going to do all the time is I jumped right to the skeleton. Sorry, Megan, you know I love you, right?
Yeah, it's okay.
Yeah, I just love picking on you because I totally relate to some of the things you do. All right, so let's do this. P, it's a valence of 5. There's times 1 is 5. And then we've got O. There's 4 times 6, and that's 24. And I already, because I've been doing these for decades, I'm like, oh crap, it's 29. Please God, let, oh, thank goodness, there's an odd number up there. All right, so electrons, we know that there are 1, and there's 3 of these little devils. So we put that on there, and we end up with, what is this, 32? Is that right? 34, let's see, 5, 29, 32. Cool. Okay, 32. Well, I can deal with that. So phosphorus goes there, oxygen, 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 oxygen. There you go. And then we'll put some clothes on these little guys. So I'm trying to, this is the fulfill the octet rule for the outer ligands, L-I-G-A-N-D-S. And right away, if you're unlucky or haven't been paying attention, go, okay, I'm good to go. Here's 8 times 4 is 32. I've got 32 here. This is my answer. This is phosphate. I'll put a bracket around with 3 minus, and I'm good to go. Well, you'll be wrong, because the next step is the formal charge fulfilled? And now the formal charge is just, in other words, are the appropriate number of electrons allocated to the atoms in here that make sense for the number of valence electrons. So I'm going to show you the math, but before I do that, how many valence electrons does phosphorus have?
5.
5. And how many, in this drawing that I've done here that I'm so proud of, how many electrons can I allocate to phosphorus?
4.
Yeah, because one of these has to be allocated to this oxygen, the other one has to be allocated to this phosphorus. So I can allocate only 4 electrons. Now, what phosphorus atom have you met, walking around Little Rock, that would settle for only having 4 when it legitimately should have enough protons in its nucleus to at least attract 5 electrons? You get what I'm saying? That phosphorus is not going to stand for it. So it's going to pull some electrons toward it. I'm explaining you the chemistry and the physics as opposed to the math right now. So sure enough, it's going to pull some toward it. So here's how we do this to explain that it's a problem. We first do the formal charge for this little fella, and what we see is, okay, and how we do that is, I'll do P, and I'm going to put should, SH, if you look at, and then we'll put what they have. All right, so here's phosphorus, and then what's here is oxygen, right? In this one, oops. All right, so the should, phosphorus should have 5, but I've only given it 4. So 5 minus 4 equals -1. You really want 0. That means it would have the right number of electrons. Here, oxygen should have 6, but if you count these, you've allocated 7 electrons to it. And so what you end up with is 5, that's supposed to be +1. And then 6 minus 7 is -1. And of course, we multiplied it by 3 because we have 3 of these little guys. I should have put that on there. Sorry. So anyways, you end up with 1 minus 3, or excuse me, 1 minus 4, and you end up with -3. This is telling you that your drawing is screwed up, because there's no way these oxygens have that much power that they're going to have more electrons pulled toward them than nature says that they actually have the power to pull toward it. Or if you don't like my explanation, which is true, that's not made up, because the math doesn't work. You got to have these things equal 0. So let's do this. Let me erase some things here because, you know, I've kind of made a mess of things here. So I'm going to erase all this business here. I know I erased it, the should and the has, but that's all right. And I'll get rid of this other business here in a little bit. All right. Okay. So now I don't like what I've drawn here. So what I'm going to do, since I know that this is screwed up, is I'm going to now make a new formal chart, I'm going to make a double bond. Would you agree if I make a double bond, I'm now pulling more electrons towards the phosphorus? I sure am. And so let's do the formal charge of this one. If we do this again, we have this is 5, is what the should is, because that's 5. But now I can allocate 1, 2, 3, 4, 5. 5 minus 5 equals 0. I don't want the 0 here. Let me do this. I'm gonna, and then, and that's, I guess I'll just do it. Yeah. Times 1 equals 0. Here, 6, now we have 2 different kinds of oxygens. We have one oxygen, which has a double bond. I'll just put it this way, and this oxygen has a single bond. For the double bond, of course, they both should have 6. I mean, for the single bond and the double bond, they both have 6, but 6, here, this double bond, how many electrons can I allocate toward it? Everybody look at this and tell me how many electrons we should allocate toward it.
There's 6 in the double bond.
Yeah, 1, 2, 3, 4, 5, 6, because you got to cut these in half. So 6 minus 6 equals 0. Ta-da! That's pretty cool. And then here, of course, these, unfortunately, I have to allocate 7. And again, there's how many of these left? There's 3. This is 6 minus 7 is 1 times 3. If I had a board, I'd write this clearer than I can do here. So this will give me a -3. So you're going to fool yourself and think you're done. But the last step is for formal charges, you want to make sure that the formal charge is definitely maximized or optimized for the ligands for the things, especially if they're very electronegative, which is oxygen, which means we're going to do one more double bond. Okay. And again, the best way to do this is to practice these. Oops, I just erased it, but oh well. And there we go. And now when we do it, we'll see we have 2 double bonds. And so phosphorus now, this is 5 minus 6, that makes that a -1. I have 2 double bonded ones times 2 is still going to be 0. And now I have 6 minus 7, but there's only 2 of them, so this is going to be a -2. This is a -1. So I still end up with a charge, which is a -3. But now look, how many oxygens now is the formal charge optimized on? 2 of them. Okay. So as it turns out, phosphorus has 2 double bonds. And so if you go back to the PowerPoint, you'll see that I'm just going to show you the answer. This is, all of these have, what is it, 32 electrons. So they all add up, but only one of these is right. And the one that is right is the one that's going to maximize the number or fix the number of the formal charge for the ligands. So you're going to see this is terrible because you got this -4. That's no good. Here you got a -3, and at least you fixed one of the oxygens. And of course, phosphorus is looking pretty good here. But here, this is the optimal one because you'll have 2 double bonds. And you've only violated, you only have the formal charge, you could, excuse me, you've only violated formal charge by -1 for phosphorus. So that is an example for formal charge. I'll stay on to do another problem if somebody would like me to do one.
Yes,
please.
Oh, cool. Okay. All right, here's our old friends. Let's see if we can do one here. I'm going to go see if I can pick one that I know is going to be kind of weird. I don't like that one. Look at this. When you start doing this, by the way, there's xenon trioxide. Remember I told you there's elements that, you know, that the noble gases can't bond. It's a big fib. In the 1960s, they discovered because of hybridization, you could make all these kinds of things, and they're pretty cool. All right, I want to figure out which one I want to do. All right. I think I want to do, I like sulfate. I'm just going to do, is sulfate even on there? That's a good one. I'm going to do sulfate. It's really challenging, and so let's do that one. All right. I don't know. All right. So let me go back to my whiteboard. Okay. Let me erase everything. And let's do good old sulfate. What's the formula for sulfate?
SO4.
2.
What's the
minus.
Very good. SO4 2 minus. Okay. So let's do this. The first thing, you know, unless your name is Megan or Scott Pursley, the rest of you guys have more discipline than me and Megan do. So you guys know, first thing is do an electron inventory. All right. So you're going to do this, and you're going to say, well, there's 6 valence electrons in sulfur. There's 6 in oxygen. You only got 1 of these, so you're going to get a 6. And then you got this, 6 times 1 there. Oops, sorry, 4. And that's going to give you, what's that, 24. And then you've got a 2 minus. So I've got to account for these electrons. Each one of those has a charge of -1. There's 2 of them. So I end up with, oops, that was kind of, my hand slipped. So I do that, and I get 1 times 2 is 2. 2 plus 26. So check my math on this. I think I have 32. Is that right? Yeah. So yeah, that is. That's 32. Cool. All right. So I want everybody to draw. I'm going to pause. I want everybody to draw the what do you call it? The skeleton diagram for this. Hint, hint, the one that only has one of them is in the center. The S goes in the middle. When you've drawn it, say, okay, I got it, or whatever.
I got it. I think.
Yeah, so there's the skeleton. It's called the skeleton. Okay, now let's put clothes on it. So everybody do that, and then somebody tell me when they're done. These are best for you to do as I'm doing them with a pencil. On your quiz, your quiz 2 weeks from now is going to be on engineering paper that you have to take a picture of and send back to me. Okay, that's
Captain.
yeah. What's that? You good?
Yeah, we're gonna come back.
Okay.
Okay. Captain.
What?
He said, are we ever gonna come back?
Oh, what a good question. I give about 50-50. One thing I can promise you is if we don't come back, if I can't find some way safely to demonstrate some of the labs, because we have these amazing labs that we haven't done. All of the really fun labs are this quarter, and they're really amazing learning processes. And I'm going to talk to Howard. I mean, I just can't imagine graduating a bunch of advanced chem students who haven't done electrolysis or sodium water reaction or smoke bombs or any of that stuff. So let's
stand 10 feet apart.
Yeah, we'll figure out something for how to do it, because not only are they fun, but they're just great ways to learn stoichiometry and all these things we're doing. So I'm optimistic, but I give it maybe a 50-50 shot. Let's see what happens after the 1st of May. But if I can get even 2 weeks of school, I can do a lot with 2 weeks of school, and it would all be labs, and it would be quite fun. If we don't, then what I would do is next fall, the very first part of AP Chem ain't gonna be like normal AP Chem. We're just gonna do labs, right? Because it's not just because they're fun, they're really, really good learning experiences. So, and I refer to them all the time when I'm teaching AP Chem, and I can't teach it if the students haven't done some of these labs. So if you go take AP Chem, you will get these labs. In my mind's eye, I also suspect you might actually remember them better if you don't have a summer between them, but that's another story. All right, so let's get back to this. All right, so I have no idea why I did that. I was just scribbling because I wanted to scribble for some reason. I don't know what I was doing. All right, so now we have this. So have we 1, 2, 3, 4. 4 times 8 is 32. We now have accounted for all the electrons. We've even fulfilled the octet rule for sulfur. So you're gonna look at this and say, aha, this looks pretty darn good. I think I'm just gonna put a bracket around it, put a 2 minus, and I now have sulfate. And you'd be wrong, okay? So what you'd have to do is do formal charge, which is the last step, okay? So in formal charge, we'll do this. It should minus half. So here's sulfur, and here's oxygen, and here's the should, and here's the have. Here's the should are always the valence, and then we'll put the number of these little guys on here, which I should have done. All right, so here should, well, we both know that these both have a valence of 6, right, guys? All right, and if you think about how many I've assigned them, 1, 2, 3, 4, 5, 6, 7. I don't know why I started with oxygen first, but I did. All right, and then here is 1, 2, 3. How many can I allocate to sulfur?
4.
Yeah.
4.
4. So this is a real problem. All right, and we know this is going to then equal 2. And this is going to equal -1. And then we know that there's 1 of these little guys, and we know that there's 4 of these guys. So you end up with 2, and then I have no idea why I drew that, but anyway, so -4, you add up a +2 minus 4, you get a -2, which is good. If you didn't get up with a -2, that means you did something wrong, because you got to come up with that. But you look at this formal charge, no way is nature going to allow this to occur. Sulfur is underallocated and the oxygen is way, way, way overallocated. So what do? Well, we start grabbing a couple of electrons and we make them into a double bond. So we do that. As I just showed you, I now have a double bond between this sulfur and this oxygen. And we all know that we have no idea which oxygen it is that does this, but we do know that it does occur. And now I still have 32 electrons. Now let's see what the formal charge is. And so what I'm going to do is, this is a single bond. And here's the oxygen that I'm going to put as a double bond, right, to kind of shorten it. And then what I'm going to do is erase this number here and this number here. And now I know this number is going to be 3. Is that right? And so that's a -3. I also know that now sulfur has 1, 2, 3, 5. So let me erase the sulfur. And we now have 5. 6 minus 5 is 1. So now I can do that. 1 times 1 is, of course, 1. I'm going to get rid of that line. I had no idea why I drew it. Okay, and then, oops, I might as well just erase all this nonsense here too. All right, and now let's take care of the Mr. Double Bond. We know that 6, and in this case, Mr. Double Bond is 1, 2, 3, 4, 5, 6, which is very appropriate. And we have 0. Okay, and there's only one of them, so times 1. Anyways, you put 0 in there, and you get -2. Now that's looking good. We always should get -2, but we see a formal charge of 0, and that is really good. Now, can I get away with one more 0? I certainly can, because would you agree that sulfur still doesn't have the right number of electrons allocated to it? It doesn't, because its formal charge is not 0, and we can still make this even better. So we're just going to put, I don't care, let's put a double bond there. It doesn't matter which one you pick. So we'll pick one. Oops, I just erased the whole darn thing. Oh well. All right, so there we go. There's my oxygen. I now have 2 of these. So what we see happening here is now this is like this. And then, and this is wrong. So I'll now have to put, we've now allocated 6 for this little guy. This is going to look really good. 6 minus 6 is 0, which of course makes all of this 0, doesn't it? Right? So now sulfur has the right formal charge. Oxygen, we now have 2 of these that are double bonded. So, I mean single bonded. So let me get rid of that. And we do know that there's now -1 times 2 of these little guys. So that's -2. That's looking pretty good. And then I have 6 minus 6. I now have 2 of these oxygens that have the right number allocated to that. So that's 0 times 2 is still 0. You add all this up and you get -2. I think everybody on the call would agree that I have created the scenario that's probably the best scenario where formal charge is optimized. I have 2 of the oxygen atoms that you have a formal charge of 0, and then I have this sulfur as a formal charge of 0. But how many versions of this are there? Well, it turns out a lot. And so what we'll do is, I can't draw the dashes very well. I'm going to try to tell CAPT Pursley I know that any of these locations could have double bonds. So if you go back then to the PowerPoint screen, here we are. So let me scroll back up.
Do we still do the brackets for that one though?
Oh crap, I wouldn't give myself credit for that. Well done, Emma. Well done. So as it turns out, if you kind of fool around with it and you do this with phosphate, you kind of think, well, how many different versions of sulfate can there be? As it turns out, there's 6 different permutations of sulfate. So you either have to give me an answer that has 6 different versions, or give me one version and put little dash, dash, dashes there. Of course, if I ask you how many possible resonance structures there are, you have to tell me there's 6, which of course I will, because it wouldn't be any fun unless I can torture you a little bit. So that's kind of how all these work. There's sodium phosphate there. That's kind of interesting. And there's just more refreshing your memory about Nick the Creepy Baby Camel, which of course we have to use moving forward. So here's the note-taking guide. What's due tomorrow, or the end of the week, is this note-taking guide filled out, and these guys filled out here. And you'll see I have the answers here. And if you still don't know why it is that we have this, by the way, this phosphate, that's not phosphate, that's phosphide, that's a different compound. You know, I can talk to you about that. I mean, you can go online and you just click on, I mean, anything. If you want to look at, I mean, just anything. Let's go to the web here. I don't know, something weird. You guys should see my browser. I don't know. Here we go. Nitrate. That's kind of an interesting one. Let's see what happens with nitrate. Lewis structure NO3 minus. All right. And right here, first of all, if you just want to look at the answer, you know, you just got to look up. Here we are. Wow, here's the commercial. Great.
Gotta love Walmart.
Right. So this guy will explain this. You can see the guy's doing this. I'm sorry, I don't know how to mute him while I still talk, unless also muting myself. So,
Little
right.
video.
Yeah, well, I'll figure it out later. So anyways, and then this guy, he does a formal charge thing. And he does it a slightly different methodology where he adds plus, minus, minus ones this way, but it's still the same math. So there's tons and tons of these on the internet. So you can figure out, well, what? How did they do this? But you can kind of see, in fact, let's just see what he has to say.
I can't hear the video if it's
All right, well,
playing.
that's good. Then it doesn't matter. It's just driving me crazy. All right, cool. All right. Oh, that's right. For Zoom, you have to use a different setting to get the audio. Not that important. All right. So going back then to the PowerPoint, what other questions do you have?
In the email you sent out, you said that some of the labs you for sure wanted to try and do at school, not just like the smoke bombs and stuff, but you said that because we have the molecule
Yep.
stuff at school, that'd be easier.
Yep.
I think out of all this stuff, I was gonna say that would be like the easiest one to try and do at home, right?
Yep.
Is there any way that, like, we could try and do that one at home if we don't end up going back?
Yeah, the trick is, you know, like for molecular geometry is what I was referring to. Unfortunately, I need the models, and they're at school. I could get them pretty easily. And we'll see what happens, whether or not the school will get reopened again. And I can show you the models and how I build them. But the best way is for you to put your hands on them so you can see these electron clouds. So
Because aren't there some websites that like we can access that would pretty much do the same thing? Not like actually touching it though.
Yep, yep. There is one for molecular geometry, and if we can't get access to the model, let's do that. That's a good idea. So let's see, what do we call those things? PhET, molecular geometry. I don't know how to spell it, but let's see if there's a PhET for that one. Yeah, here's one. Let's see what happens. That one's not good. Oh, this one might be though. There, we'll first have to teach you Vesper here. This one, let's see how good this one is. This, I don't like this PhET. This is like for 8th graders. It's no good. So I'd have to find one. It might be this one. I don't know. This, maybe. Yeah, you actually, I see. No, that's not electron cloud. I'm looking for electron cloud. There's an electron cloud. I might be able to use this one. I don't like it very much. I'd rather use the models because then you put your hands on them. You haven't seen those models. I haven't used them yet. They're not the little balls. They're in the back of the room in the closet. Okay, well, I'll figure out something. Because I won't allow you to finish advanced chemistry without doing molecular geometry. So it might be your idea, Megan. I might have to do it with a PhET. All right, any other questions? Okay. Then I will see you guys or talk to you, maybe some of you tomorrow. If not, then I will talk to you next week. Remember, at the end of the week, what I need you to do is upload your note-taking guides with the practice you've done. These are really important to get full credit. You have to do them all. You will have plenty of opportunities if you can't get this right answer to reverse engineer it yourself or to go online. Lots of examples. That's how everybody does it in advanced chem. And then we'll be ready to go into the next unit, which is whatever it is after this one.
Question?
Yeah.
We don't have to show the 2 charts for all of those, right?
You don't have to show anything.
Okay, we just have to write down the answer.
Yeah. Yeah.
Okay.
If you want, you can fill out your stuff here until you run out of room, right? You'll learn, except for Megan and me, that if you just kind of start in and start drawing them in here without doing the electron inventory, the wheel's gonna fall off your work pretty quickly. So anyways. And then we're gonna skip molecular geometry. Next week we start IMS, which is really a review. And then we jump into types of chemical reactions, which are pretty interesting. So, but you'll see for molecular geometry, how important it is to me is there's 1, 2, 3 pages worth of stuff in here. There's a lot of knowledge that you guys will get when we do molecular geometry, but I don't want to do it next unless I can get those models. If not, then we'll just jump back to it and do it using PhET, okay?
Hey, Captain, this is unrelated to this at all. I still have your present that I never gave you, and then we all got quarantined. So it's just like sitting right above me right now.
Yeah?
Is there any way that I can like give this to you?
Totally. Yeah. Why don't we go offline and we'll figure out some place to meet and, we'll do all that social distancing stuff and we'll get it done.
Okay.
It'll get me out of the house.
It's not like... It's funny. It's funny. That's literally it. There's like no, there's like nothing else to it.
Great. Okay. Any other questions? Okay, guys. I'll talk to you later. Bye-bye.
See you, Captain.
Bye.
Captain.